point to something, so total 6 block. Plus 1. Why? Because to search the index key entry is the total 6 block. Plus, we need to access the data file. 1 block is total 7 block. So, 7 block is faster than the 12 block. What if we have the more data? The gap will be the wider. Okay? So, that is a benefit of using index. That is a single level index. Why? We have this is a data file and one level of index. So first, the index was the primary index. Second is a clustering index. Clustering index means why don't we make the index for the group thing? Group the column. For example, here, this is a department employee table. But it's ordered by the department number. It's not unique. Department number on employee table is not unique, but we can make the order, right? So this is ordered file for the employee, but ordered by group, the index. It's a non-unique, the column. So 111, 222, 33. So we don't have to keep all of this. It's the first one. Okay, as the anchor. 1 is block, and 2 starting here, 2 the same pointing same block, and 3 over here, 3 at the block, and so on. Question: is this the dense index or sparse index? So definitely sparse index. Okay. Then how can we search the index over here? First, binary. We can apply the binary search. For the index, then using pointer, we can access the data. Okay? You may be curious, why don't we separate the, for example, here, the second block has number 2 item and number 3. And this one has 1 and 2. So they are mixed. So if you don't want to mix the data, this one in the column, you can make this. Okay, it's not a problem. This is more popular. So in this case, it's a clustering, but for the same value will be same. What if we have the more data larger than the blocking factor, for example 3? At that time, we can point to other the block. Then we can make. However, if we use this one, it's not easy to point. The next one is the secondary index. So for example, the data file is not ordered. Okay? For example, this one is not ordered. Then we can make the index for this. Same idea. Okay? In this case, question, is it the dense index or sparse index? It's a definitely dense index. We need to have the whole pointer for the index key value. What about the textbook index? Is it dense index or non-dense index? It's a definitely non-dense index. Okay, sparse index. But here, this is the dense index. Why? Because they are not sorted, so we should have the whole pointer. Okay? How can we search the data? Same thing. We can apply binary search for this, then +1, and access the data. So we can do the same math to calculate the complexity, how long it takes. So, for example, if you are not using the index, it will take the 1,000, because it's a linear search, half of the block, so 1,500 block. But if you are using the index for this one, so 9, total 9, so 9 plus 1, 10. Huge difference. So, this is the idea of what? Query optimization also. So query optimizer is the algorithm to decide the fastest. For example, when you travel, so you search the Expedia.com, you search the what else? The hotels or whatever. Then you have your criteria to decide the best offer. Most of the people, price. But sometimes time, quality, whatever. So let's say the price, this is the price. Less price is the better. Okay? So that is the idea of the index. So in case of the non-key field, which means that this one, it's a non-key field, okay? Non-ordered file. In case of the non-ordered file, there are different options, okay? We can make the index for the like the previous example. Make the index for the key. And also another example is like this one. Why don't we make so this is a non-key. So one may have the several values, one over here, one over here, one over here. So you can have the multiple pointer. Okay? So for the multiple pointer, you can have the one pointer, one pointer, one pointer. Or you can make the array. One pointer block number 0, block number 1, block number 2. Like that. So there are not much difference, but you can. It's a part difference in when you implement the index. Okay. Another way is you can make the extra level for the pointer like this one. So this is another level. Okay. It's not actually part of index, but it can be considered. Okay. So they are but still, even though we are using another level, index itself is the one level. So these are so far we have talked about single level index. The problem of the single level index is, what if we have more data? Index size will be bigger. The more index block we have, the more index block we have, the longer time. It will take a longer time. Why? Because we are using binary search. So logarithm actually is increasing the graph. So increase function. We want to increase the graph. So what if it takes a longer time to access the data using index? It takes a longer time. Then what can be the solution? We can make index of index. We can make the index for this one, like for example 1. We can make the 1 point here, and 9 point here, 17 point here. Okay, so we can make the index of index. What if this one is growing? So we have more level of the more data blocks for this one. We can make another index. That is called multi-level index. So multi-level index is the index of index. So for example, this one. How can we search the data? Apply the binary search over here. Then go to this one and apply the binary search and go to this one. So that's it. So this is an example to design the complexity of that multi-level index. I believe you guys can do this one. Okay? Then eventually, if we generalize the multi-level index, so multi-level index is like this. Oh, not this one. Where is it? Oh, yeah. So let me simplify. So this one is a node, and this one is the block, right? This block. Then block 2, 3, 4. Like this, right? So what if we have multi-level index like this? What is this? Have you ever seen such a data structure? Graph? If you rotate 90 degrees to right, it will be a tree structure. Yes, it's a graph, but you can see some parents and children. Because we need to access this one first, then next, and next, finally, the data. So eventually, multi-level index will form a tree structure. So that is this one. Okay. So many of the actually the indexing structure are most of not hash is a different one, but the other is mostly based on the tree structure because of this reason. So this is a tree structure. Then how can you access the data? We need to access the root first. Then check which one is a child node that belongs to the data. So let's say the P. Then P, then F and J. Then this has the pointer for what? Data. Okay. So how many IO do we need? 1, block 1, 2, 3, 4, and finally 5. Okay. If we access the data through G, 1, 2, 3, 4. Okay. So we can speed up to access the data using search tree. That's very convenient, the indexing structure to access the data. There's one huge problem. It's actually the most of commercial, the DBMS database system, they don't use the search tree. What can be the problem? Level is increased, which means it can be easily skewed data. The skewed, why the skewed data, skewed tree will be problem. Skewed data means the extreme case we have this one, this one, this one, this one. Why? This kind of the skewed tree structure is a problem when we search, when we access the data in DBMS.
Because it's going to become linear.
It's going to
Become linear.
linear. Yes. Why linear is a problem?
Because complexity is n over 2. We want to be
Yes.
log. Okay.
The complexity. So even though sometimes takes this time, if you are lucky, 1, 2, 3. But when we calculate the complexity, it will be this one. In other words, so we have two websites to this when you travel. Okay, we have the two websites. One website says if you are lucky, sometimes it provides very cheap price, but sometimes like the hotels.com. I'm not sure what nowadays. I didn't use the hotels.com. Hotels.com they hide the price, but they give the range. They give the price, but not the hotel name. Okay, so once you pay, then they show the quality and the price and the name of a hotel. So you cannot guarantee the quality of your hotel. But another one is slightly expensive. Okay, but they guarantee the 3-star level hotel or 2-star level. Which one is preferred? In my case, I like this one. Okay, because even though this one is cheap, but sometimes comparing to by considering the quality of the hotel, it's not the best price. Another example is when you travel from Bridgeport to the Manhattan. How many different ways? So many different ways. So let's say we have two of them. One is driving using 95. Another one is MTA. Which one is faster? If we do not have traffic, driving, that's like the 100 miles per hour. Okay, then it takes less than an hour. What about the MTA? Always 1 hour, 50 minutes. Okay, 75 minutes to the Grand Central Station. Which one do you prefer when you come to my classroom? Definitely MTA. Why? Because it's guaranteed. Driving, if you are lucky, it takes the less than an hour. But if you stop in the middle of the highway, it will take the 2 hours, 3 hours. It cannot be excused for the midterm exam. Really, that's not a joke. It's real. It cannot be excused. Okay? It's your responsibility. So, which one do you prefer? Which one do you use to decide your travel? It's the MTA. It's the same thing. When query optimizer decide whether this index, we have the two index. this one, and this one. Query optimizer want to use this. Why? Because it's always maximum 4. Then plus 1, 5. The node, any block is less than 5. But this one, if you are lucky, it's a 3. It's better than this. But if you are not lucky, it will take 1. It's not guaranteed. So query optimizer really hates such a non-guaranteed data structure, indexing structure. So this one is a preferred. So this is called balanced tree. Because of that, B3 is called balanced tree. So this is just a search tree. It's a general search tree, and this is a balanced tree. And DBMS use such a balanced tree for indexing structure. Okay, so let's take a look at a little bit more search tree. As you can imagine, this is almost the same as the binary search tree. Binary search tree is less or higher, lower or higher. But here the search tree has more than binary. Okay, so what does that mean? PK. P indicate pointer address. K means it's an index key entry. For example, here. So let's say this one is the block pointer to this, pointer to this, pointer to this. Then this is a 10. This is a 20. Less than 10 goes to this subtree. Okay? So this is a key value. So less than 10 goes to here. Between 10 and 20 goes to C, children. Higher than 20 goes to D. And B has the same structure. Pointer and key. Pointer and key. So less pointer, this one is the E. Okay, children pointer. Then this is a 5, let's say. Less than 5 goes to here. This one. Higher than 5 goes to here. Okay, another subtree. F has the same thing. Pointer, key, pointer, key, pointer. And this one, same thing. Pointer, key, pointer. You can generalize a number of key and number of pointer. However, always key is 1 less than number of pointer, right? Because children pointer, children pointer, children pointer, children. In between we have key entry. So that is a search tree. In binary, binary is what? Only one key. Less than 10, higher than 10. And this is the pointer. Pointer. This is a binary. Search tree is a generalization of such a binary search tree. Okay? At that time, the number of that will be discussed later. Okay? So this is an example of the tree structure. What is this one? Rectangular box. This is a block. Okay? So one block. Okay? Index block. Then this one is called node in tree structure. Okay? So sometimes I'm saying the node for the block in indexing structure. But it's this one, the triangle. It's a subtree. This one has also same node structure as a pointer, key, pointer, key, pointer, key, pointer. Okay. Then this one has the also like the subtree and subtree. Okay. So this is an example of the search tree. So one node indicates one index block. So in this case, how many pointer per block? How many children this tree structure can have maximum? How many children? 2. One more, 3. But it's not used here. Okay? So there are 2 key, index key, per block, per node. How many pointer? 3 pointer. Okay? So this subtree has less than 5 goes to first child. And bigger than 5 is the second child. If we have the 20 here, between 5 and 20 goes the second child. Higher than 20 goes to the third child. So this might be 22, for example. Yes?
So those keys like 5 and 20 are like big ones to determine where to go.
Which one?
5 and 20.
5?
5 and 20. Those are like big ones.
Yes, this one is useful to decide the subtree. Okay? So for example, when you search the data, let's say the 7, okay? Check here. 7 is bigger than 5 and less than 20. Okay? So which means this pointer. Go to this one and check. 7 is bigger than 6 and less than 9. So goes to this one, finally 7. Okay? So this is a search tree. This is actually simplified. So you need to understand each key entry. So we learned the key plus pointer, right? So each key actually has the another pointer, like this one. What kind of pointer? It's the data block. Okay? Data block pointer. So when you search the data, for example, this is the social security number 1, 2, 3, 4, 5, 6, 7, 8, and this one. Then when you search 8, Lee, 8 is bigger than 5 and bigger than 6, less than 9, and goes to here. Then 8 has the data pointer that point to this one. So how many are you to access this record using index? 1, 2, 3, plus always 1 more. So it's a 4. Okay? So what about 5? This one is the pattern. To access the pattern using index, 1, then using this pointer, 5, 2. Okay, always plus 1. So that is a search tree. At that time, order P means number of pointer. And 1 is the number of key entry. Key entry is P minus 1. Okay, so this is the search tree. We already checked the problem of the search tree. So it can be skewed data, right? So how can we address that problem? In other words, how can we make such a tree structure to the balanced tree? Any idea? Any idea how can we make it balanced?
If we define the height of the tree.
Define the height of the tree. What if we have more data? It will be growing. It will be growing. I will give the 2 minutes. Why don't you think about the solution? How can we make? Hint. How can we make the search tree? First, you need to check the root node. Then next and next, if you need it, add up to the leaf node, right?
First, we need to check the root node,
Mhm.
and if the next entry is less than the root node, then we need to search to the left side of the
Mhm.
to the left pointer of the
Mhm.
root node.
Mhm.
If it is greater than the root node, then to the right side.
Mhm. That is a search tree, right? That is the same as the search tree. I think that you are thinking of a little bit close to the answer, but still that is the idea of the search tree. Any other? So we can say search tree is a top-down approach because you need to access always the root. Then growing up to the down. Going down. Right? Because of that, it will be skewed, right? It can grow up, grow up, grow up, grow up, grow up. So, our solution may be opposite. Which means bottom up approach. We are not going to make the tree grow up top to bottom. Instead, bottom to up. Which means root will be leaf node always. So first, one, if in tree we split, not split, we make another node in case we need the space. Instead, if we need the space, we split. Then growing. Still two. If we need more space, split and growing up and make it. Always 3, 3, 3. That is the bottom up approach. That is the special case of tree structure. It's called B3 index, balanced tree index. So next topic is the B3 and B plus tree index. First, we are going to take a look at B3 index first. So B stands for balanced tree. The B plus tree means, plus means it's kind of an enhancement. Okay? So if you understand the B3 index, B plus tree is not very complicated. But in practically, the B plus tree is most popular. Much. So very few number of DBMS use the B3 index. Most of them use the B plus tree. Most of commercial one use the B plus tree. You need to understand the full of the node. This is the one block node. This is a pointer, and key. So let's say we insert 1 and 10. It's okay. So index key entry 1, index key entry 10. What if we have 5? In case of the tree, we can make the children. And we can put the 5 over here. In B3 index, in case of full, this is called a full. If we need more data and more space to insert the index key, we split into 2. 1, 5, 10. Okay? Then half of them goes to here, half of them goes to right hand side. Then make parent node. Instead of making the children node, making the parent. This one is less than, equal or less than 5. And this one is bigger than 5. So we can create this one. This is the idea of B3 index. It's a bottom to up. Okay. At this time, this is called split. There are two operations. Split operation. Split means in case of full of the node, we can cut in a half and left and right. It's a similar idea that you mentioned. So in case of group of making the children node, make the sibling left hand side, right hand side. So copy, then split into 2. Actually half and half. Okay, half and half. But when we have odd number, we can exactly half and half. But when we have the even number, so middle value belongs to left hand side. Either it's a left to or right, but in our case, So we are going to use the left-hand side. So 2 and 1. And make this is called the split. And this one is called promotion. Promotion means the middle value will be used for key to separate the data. Okay? So exactly opposite of the tree. Tree, you make the children node. But here B3, you make the parent node. That is called the promotion. So two operations. Split, when in case of full of your block, the block is full, so split into two. Half and half. Okay? Then the middle value will be promoted. Why? Because we need to make the parent node instead of child node. So that is the B3 index. So this is the node structure. Node structure. So it's similar as the tree structure. So we have number of pointer. How many pointer? Q number of pointers. So order is Q. And how many key entry? Q minus 1. Right? The P. Then each key has another pointer. This is a pointer of what? Data pointer. Okay? So we can simplify. So this is a good example. So Q is order is 3. So which means P is equal to 2. Then first thing you need to do is decide the node structure. How many pointer? 1, 2, 3. And how many key? K1 and K2. And this is the data pointer. This is our data structure for what? Index node. Okay, in B3. So then we are going to insert this number 8, 5, 1, 7, 3, 12, 9, 6. Actually, when you insert the data, you are not going to insert only the key. Probably insert into, so let's say this is EMP values 8, Lee, and other information. But we are going to simplify. Okay? Only focusing on the index value 8, 5, 7. Okay? Then this is the order to insert the index key value. So what if 8 is inserted? It's a first value, so we can create empty 1. So 8. Okay. The next